Welcome back. So the next talk is Breaking the Sound Barrier by Dillon Franke. Enjoy it.
All right. Thanks so much, everyone. Thanks for the introduction. Really nice to be back in Berlin. I studied abroad here in college, so always a pleasure to be back. Thanks for OffensiveCon for putting on this conference and inviting me, and thank you all for being here. I'm really excited to talk today about some macOS fuzzing security research I've been performing over the past year and a half or so, looking at fuzzing Mach messages and how they interact with different processes and how we can abuse memory corruption there to find sandbox escapes. So a quick little bit about me. My name is Dillon Franke. Spent some time at Mandiant, originally doing red teaming, pen testing, focusing kind of on application security and source code reviews, embedded device assessments. Also really got into reverse engineering, spent some time working with the Flare team there, doing malware analysis and exploit in the wild research. And currently, after the acquisition, I just recently moved to a new team within Google, doing security research and product security reviews, as well as 20% research with Project Zero, which has been great. So that 20% project is what I'm going to be talking about today. So this was candidly my first venture into the macOS fuzzing and exploitation space. So I really hope it, first of all, serves as inspiration for those who are interested in this research space. But I hope it's also useful technical content for those who are more well-versed in the macOS research community. So my goal is to quickly build up some background knowledge and shift to deep technical content after that. So I'll start with a quick crash course on fuzzing and Mach IPC. Then we'll talk about kind of the attack cycle that I used and went through throughout this research. Then talk about some vulnerabilities I found, exploiting them and patches, and leave some time for Q&A. So the way I like to define fuzzing, just as a very basic definition, is sending unexpected inputs to a system in the hopes of making something unexpected happen. Most of you know what fuzzing is. Most of the time when we're fuzzing, we're wanting to trigger crashes so that we can exploit memory corruption in memory unsafe languages. But you can use fuzzing for a lot of different things. We heard in the parser differential talk earlier, you can use fuzzing to try to find those. You can use them to find logic issues. But today we'll be looking for crashes and trying to exploit memory corruption. So when a lot of people think of fuzzing, they might be a little turned off to it. They think of it as kind of high level, not really getting into the weeds and kind of just sending random input and hoping it crashes something. I tried to take an approach that I like to refer to as knowledge-driven fuzzing in my research. So this is a blend between automation, which is your fuzzing, and that allows you to quickly identify interesting inputs without really understanding the code base yet, and kind of use that move fast and break things mentality that we like to talk about in the San Francisco Bay Area. And then you combine that with more manual analysis. So as you're fuzzing, you look at the code coverage and you say, okay, why is this plateauing? What assumptions have I made that are invalid? Or what initialization am I not taking into consideration here with my fuzzer? And then this allows you to develop a more deeper understanding of the code base and kind of build up your knowledge as you go along. So I think these two auditing approaches work really nicely together. So the kind of attack cycle that I used here was first, I needed to identify an attack vector here, choose a target, create a fuzzing harness, fuzz and produce crashes, then analyze those crashes and look at the code coverage, then iterate on that fuzzing harness. So understand what invalid or bad assumptions I was making with my fuzzing harness and improve it. And then at some point, hopefully generate some security relevant crashes and then work to create an exploit. So the first step here was identifying an attack vector. For this research, I chose to look at IPC and specifically how they could be abused for sandbox escapes. This is not a new technique. They're used very frequently for this purpose. And they're really useful because modern browsers are all have a strong sandbox, and so in order to really make use of an RCE in a modern browser, we need that additional sandbox escape vector. So IPC mechanisms can serve as a natural bridge between these restricted and unrestricted processes. Mach messages have a ripe history of abuse, linked some really good research here, some of which was done by Ian Beer, talking about how you can abuse Mach messages both for heap grooming and sandboxes and privesks in the past. This blog post from Ret2 Systems was also a great inspiration for me. They walk through the full process of building a Safari sandbox escape for Pwn2Own 2018, and wrote a really nice research post about that, so recommend that as reading as well. So before we can talk about Mach messages, we need to understand Mach ports. And a Mach port is really just an IPC message queue that's managed by the kernel. So there's this notion of a port write, which is a handle to a port that allows sending or receiving messages to that port. And you can either have a receive write or a send write to that Mach port, which means you can send messages to that message queue, essentially. So as a basic example of how you would establish a Mach connection, so there's this thing called the Bootstrap server on macOS. It's a special Mach port that helps establish connections with other Mach ports. And by default, all processes can send Mach messages to that Bootstrap server. And so if they want to look up a service name, say they want to look up com.apple.offensivecon, what they can do, Alice can allocate a new Mach port with a receive write, and then Alice can register her service using a specific name. And by registering with the Bootstrap server, she's saying, okay, Bootstrap server, I'm giving you a send write to this port that I have a receive write to. And then Bob can come along and say, okay, Bootstrap server, I want to send to this service name, and the Bootstrap server can give a copy of that send write, and then Alice and Bob can now send messages to Alice's Mach port, and Alice can receive them. Cool. So I wanted to look at Mach messages here. They're the lowest form of IPC on macOS. The next step was to identify a target. So identify a place where these Mach messages were actually being ingested and where I could send fuzz input to. So all system daemons on macOS, or most of them at least, register Mach services using launchd. This is in charge of bootstrapping all of the system daemons on the operating system. And so there's plist files that are stored in the launch agents and launch daemons directory. You can see an example here. This is a Mach service exposed by the address book application. So all these will be specified here. We can use this to enumerate services that we can interact with. Then I wanted to find sandbox allowed communications. So I looked for high impact sandbox processes that we would like to break out of, like web browsers or maybe Acrobat or Microsoft Word, analyze which Mach services they can interact with, and then identify the binaries that are implementing those services. So you kind of end up with a ton of processes at the top level you could target, but then you filter it down to the ones with just a Mach service, and then furthermore to ones with a sandbox allowed Mach service. So it kind of helps hone in our target here. So to find these sandbox allowed communications, one way you can do that if they're using Apple's App Sandbox is by looking at these SB files, which are written in the tiny scheme format. So if a service is allowed, or if a sandbox is allowed to send Mach messages, you will see this allow Mach lookup permission within that SB file. That means they can look up the service name and interact with it. Another thing you can do more dynamically is use the sandbox check function, which is a built-in function. Jonathan Levin has a nice tool you can compile and use to determine which services a process can actually send Mach messages to. Cool. So after enumerating kind of all of these interesting services that I could talk to from web browsers and other highly privileged processes, I identified the CoreAudio daemon, and I chose it as a target for a few reasons. It contained a pretty complex service called the audio HAL-D, And it also allowed Mach messages from several impactful applications, including the Safari GPU process. And the Mach service had a large number of message handlers that were kind of exposing functionality through a RPC-like interface. I also thought, since this is sort of probably managing the audio hardware abstraction layer, it's likely going to need to control audio hardware and is thus going to have elevated privileges. And then finally, the CoreAudio debinary and the CoreAudio framework that it uses are both closed source. So I thought it would be a unique reverse engineering challenge. So the next step here was to create a fuzzing harness, which is just code that allows you to send input through an attack vector or call a desired function. The entry point really matters here for where you're actually going to send your fuzzing input to. Fuzzers are highly capable of finding more than just surface level bugs, especially if they're properly implemented and using coverage-guided fuzzing. But it only works if the fuzzer's energy is focused in the right place. And so finding that right place to fuzz is highly dependent on the target and the situation. Sometimes you trade off the ease of development for your fuzzing harness versus running it in an unrealistic environment. Sometimes you want increased performance, and you're okay with taking more false positives because of the increase in performance, but it's very highly dependent on the target and research goals. So in my case, I thought of a couple options of ways I might want to build this fuzzing harness. The first option I thought about was an inter-process message send. So the way that you send Mach messages naturally is using the Mach message API, and that's going to send your message to the kernel, and it'll dispatch it to the proper service. So what I could do is write a harness that just continually calls Mach message with the fuzzer provided input. So the pros of this, it's very simple to write, and it's similar to how you're probably going to be exploiting or triggering the vulnerability when you find one. But the cons are that it's very slow because you're at the mercy of the application to send messages or of the kernel to process them. And there's also many points of potential failure along the way. And most importantly, I think you're dealing with two different process spaces. So getting code coverage and understanding how much of the program or the target you're actually exploring becomes very difficult. It's also difficult to determine which message actually caused a crash. So the other option here was to use a more direct harness. So load the code that actually implemented and handled the Mach message processing, and then call those handlers directly with the desired input. The pros here would be it'd be much faster, and it would also be in the same process space, so we could instrument and collect code coverage more easily. And we also are very easily able to correlate which input caused a crash and replicate it. There are some cons here, though. It's going to be, our payload that we're sending when we're directly calling a Mach message handler is going to be different from the end exploit. And as we'll see, we might have to invoke some initialization routines. So I ended up choosing the second option here, the direct harness, mostly because of it being in the same process space and being so much faster. So the approach here would be to first identify the Mach message handling function in the CoreAudio daemon service, write a fuzzing harness to load the message handling code from CoreAudio, use a fuzzer to generate inputs and call the fuzzing harness, and hopefully we'd profit from that and get some interesting crashes. So I started looking for this service, this audio hald within the CoreAudio binary, and did not find any references to it. So I looked at the libraries that it loaded in and found the CoreAudio framework was one of the first used. I wanted to pop that open in IDA Pro, but interestingly, the binary was not on the system. And those of you who do macOS research might know about the Dillon shared cache. So starting with Big Sur, most framework binaries are not on disk, but for optimization purposes, they're stored in this special cache that can be extracted. IDA Pro and Binary Ninja, I know, extract them automatically. You can just pass in the cache directly, but there's also extractors out there as well that you can use. So once I started looking at the CoreAudio framework, after I had extracted it from the Dillon shared cache, I found this audio HAL-D service that was being registered with the Bootstrap server. So we had found our Mach message handler. It still wasn't super obvious exactly how the message processing was happening, though. And as I looked more into this, I learned about the Mach interface generator, or MIG. It's an interface definition language that abstracts away a lot of the Mach layer. And you can actually grep for these things called MIG subsystems and get a good idea of where the message handling code is going to be happening. So if we actually look for where this is used in the binary, hopefully you can see this okay. I identified where that MIG subsystem was being used, and it's basically being used as a sort of message lookup table where it's processing a message ID from the incoming Mach message, getting the subsystem offset, and then indexing and calling a function. Cool. And then this leads to a bunch of different, about 60 or so RPC functions that we can actually call through this Mach interface. So the next step here would be, ideally I could just load the CoreAudio library and call that MIG server function, but it's not exported. So I borrowed some logic from Ivan Fratrick and his TinyInst library, which we'll definitely be talking about much more later. And there's some logic in there that can parse Mach-O binary headers and load commands and extract symbol info. So we could use that to resolve and call that target function. Cool. And I recently open sourced the fuzzing harness and some of the tools used in this research, so I'll provide links to that at the end. But the full fuzzing harness can be found here. But basically, here we're just reading in a message from a file and using it to call that Mach message handling function directly. Another important thing here, coverage-guided fuzzers will mutate and identify good inputs for you over time, but a seed corpus is often helpful to kind of kickstart things and get the ball rolling, so you're not just sending, random data to your fuzzer to start with. So I used a Python LLDB script, hooked onto that MIG handler, and then just interacted with the system. This audio MIDI setup application for macOS was pretty helpful, actually, because you can create new audio devices and set audio settings pretty easily, and harvested those messages to feed as that initial corpus to the fuzzer. So now is actually time to fuzz. For my fuzzer, I used the excellent Jackalope fuzzer, which was once again written by Ivan Fratrick. I liked it because of its high level of customizability. And also it just worked out of the box on macOS, very nice. And it's got a great code coverage instrumentation framework called TinyInst, also by Ivan Fratrick. You might be noticing a trend here. And it's a lightweight dynamic instrumentation binary that is really great for getting code coverage in this case. So immediately once I started fuzzing, crashes started happening. But often these initial crashes, especially when we're hooking or when we're sending input deep into a function that is not expecting to be sent there, we are probably not getting security relevant crashes at this juncture. They likely indicate a fuzzing harness design issue or some invalid assumption that I made in writing this harness. So this starts this process of iterating on the fuzzing harness and slowly improving it to kind of solve or get past some of those assumptions we've made. The first invalid assumption I made is the target initialization. So normally when CoreAudio D starts up, it calls some initialization functions, sets up hardware, does some other things, and then it's finally ready to process Mach messages. But what I was doing with my fuzzer and harness was just immediately calling the process Mach message function. So clearly there's going to be some issues there. And code coverage that you're getting and error messages can be very insightful here. We're getting this there is no system message every time in this Mach message handler. So you can start to look into the code coverage and look in IDA and figure out, okay, why am I plateauing here and never increasing code coverage? So I was able to just call a couple initialization functions in my harness and get past that. Another bad assumption I was making is that all Mach message handlers functioned independently of each other. So one example here, you see I'm calling this object set property data API, and it's telling me there is no client. So clearly this API expected some previous message to be sent that would initialize things. And this kind of calls out a need for what we call structured fuzzing. And this is the idea that most fuzzers only accept bytes. But what if we actually consume those bytes as a stream and then use them and dispatch them to do different things for each input? Ned Williamson had a really great talk at OffensiveCon 2019 about this that I've linked here. So I use this kind of idea of structured fuzzing to implement what I refer to as API call chaining. So we take a single fuzz input, which is just bytes that we've read from our corpus, and then we use it to actually dispatch multiple Mach messages. So it's pretty simple here. We're using the fuzz data provider to loop through kind of the rest of our input, and then based on the message ID that we have in that input, we'll send a message, and we'll actually end up sending multiple messages per input generated by our fuzzer. And this might seem really simple, but it actually is really powerful in practice because you basically you allow the code coverage of the fuzzer to inform you the order in which to send Mach messages. So you have this sort of stateful system that you can almost get information from the code coverage about. And so it can tell you very quickly, like as I wrote this harness and started fuzzing, it told me, oh, you actually need to send this X system open message first, and then you need to register a client before you can send maybe this other message. So pretty powerful concept, but very simple and easy to implement in practice. Another harness iteration that I made here was mocking out functionality that wasn't important or was even buggy, but not security relevant. One way you can do this is through C function interposing, and the example I used this for was overriding the custom the bootstrap check-in method. So I was getting issues with my harness because it was trying to register the audio HAL-D service again, and since that was already running, we were getting some errors that we obviously needed to address. So we can create a custom bootstrap check-in that basically just tells it, hey, everything's good, return current success, and we don't have that issue anymore. Another example here was kind of a silly bug where it was accepting a property list, a specific API that we could send data to was creating a property list from data, but there was no check to see if it was null after it was created, and then it would just call CF release on that, which just calls a abort on macOS. So this is not a security relevant bug, but it was really messing up efficiency, and so I needed to address this. To do that, since it's a C++ function, it was a lot easier than doing interposing to use the TinyInst hook API, which is really nice, kind of similar to Frida in a lot of ways, where you can say, okay, when you enter this function, perform this logic, and you can also have custom code fire when you're returning as well. So this just looks to see if the third argument here in the RDX register is null, and then basically if so, it will just return early so that it doesn't call that CF release. And that works well. That increased my fuzzing efficiency a ton and helped me to just get through that process where I wasn't increasing code coverage. So the full custom fuzzer implementation with that TinyInst script instrumentation is available in the Project Zero Tools repo as well. Perfect. So we've talked about kind of the setup and how I designed the system and the approach I went through when fuzzing. Now let's talk about actually finding and exploiting some vulnerabilities, which is what we're all here for. So a little background, I want to just talk quickly about the hardware abstraction layer. This is a layer on macOS that allows you to interact with audio devices, plugins, and settings. All the information is stored objects on the heap. It's a linked list of these things called house objects. And as you can see here, here's one of them that I'm dumping. I use the TinyInst hook API once again to just find the linked list in memory and then iterate through all of them and dump them. So this starts to give us a little bit of an idea about where some of this audio information is being stored on the system. So when these APIs look up or modify one of these house objects, most of them use this API called copy object by object ID. And this just takes an index parameter and then goes through the linked list and returns that house object. So I saw this really intriguing crash eventually that was pretty shallow in the call chain. So I know it's a little bit small, but if you can see here, it's there's the MIG server that's firing, and then there's a Mach message handler function, this XIO context fetch workgroup port. And then the actual crash was occurring on a call instruction where we were getting a bad access. It was trying to index into the RAX register and call some function pointer. So this looked pretty interesting and looked to be a pretty strong primitive. But as we will see, it was a little bit more difficult to exploit in practice. But first, let's look at exactly what was going on here. So we talked about this copy object by object ID function. What it was doing is first fetching one of these objects from the object map based on an ID that was fully provided by the user in one of these Mach messages. And then it was dereferencing the address, we can call it A1 at offset hex 68. And then it was dereferencing that address again at offset 0. And then it was calling a function pointer. So what it was actually doing here is doing a vtable lookup. It expected a vtable and then calling a function, presumably to get the workgroup port for that object. It was expecting an IOCT object, an IO context object. And when it is an IO context object, everything functions normally. It looks up at offset 68, that pointer to the second object, and then dereferences the vtable, and then looks up and calls the get port function. But as you can see here, if we're able to influence the object that's fetched, we can potentially get it to dereference our pointer, point it to some attacker-controlled memory, and then get it to index into a malicious vtable and call a function. So this got me pretty excited. I reported this to Apple on October 9th, 2024, and it got fixed pretty quickly on December 11th, 2024. So thinking about exploitation, the first thing that I wanted to look at was there a way to write data to this offset 68 of any house object in the system? If we could do that, since we could call that copy object by ID, we could get any object fetched and then cause that flow of dereferences and calls to happen. So really, any object we could influence data there would be interesting. There were several places that we could do this. For example, when we create a new audio device on the system, we can place a UID CF string at that vulnerable offset. So you can see there it's constructing a new house object and then setting at offset 68 that UID string. And that would be controllable by us. So that looks pretty good, but unfortunately that doesn't work because the CF string type has an uncontrollable header. So there's this 16-byte header called the CF runtime base that's at the beginning of most core foundation objects. And so and if you remember, if we go back here, our kind of vulnerable call chain here performs a second dereference on that object that we point to at offset 68. So if we can't control that header, then we're not going to be able to hijack control flow here. It's going to try to dereference the CF runtime base, which is bytes we can't control. So somehow we need to write a pointer to an object that we control, and then we need that object in turn to point to data that we control. And in my mind, this was a little bit tricky. So with Yvonne's advice, actually, I ran CoreAudio D with Apple's Guard Malloc, which is a library similar to ASAN that provides some memory. You can set specific functionality like pre-scribble, which it places like AA bytes in freshly allocated memory box. So you can see when objects are not zeroed properly, and maybe they're making assumptions about the memory that's being used. And this can lead to them using uninitialized or previously freed memory, and then you can easily see that. And we thought this could be an interesting vector to look at here. So I ran Guard Malloc with this pre-scribble bit set, and immediately this engine object looked really interesting because there were a bunch of A's at offset 68. So I thought, okay, maybe this is using uninitialized memory. Maybe we can get a previous allocation there and use it to point to somewhere we control. And we can see here, if we trigger the vulnerability on that object that we just enumerated, we get that RDI register set to that value, and we get a crash. So one thing that you might notice here is the last 2 bytes there are actually zeroed properly. I'm not exactly sure why this was happening. It's probably because there was some short they were using in this object that they were setting to 0 and initializing properly, but the rest was using uninitialized memory at that address. So kind of an interesting part of this exploitation process. So the new exploitation strategy here would be to find a way to allocate a bunch of data that we control, try to create some indirect pointers to that controlled data, and then try to get our program to reuse our indirect pointers in the unclaimed memory region. Once again, that caveat being the indirect pointer will have its last 2 bytes always zeroed out. So kind of an interesting circumstance here. So I needed to find a data allocation primitive on the heap, and property lists were very useful for this. This is a widely used technique in the macOS exploitation space. So many of the APIs that I could invoke here accepted user data in the form of either binary or XML serialized property lists. And there were these APIs then deserialize the data and allocate new core foundation objects. So here's an example of one of the APIs that I could call. It's basically just creating data out of our user-provided data and then creating a property list from that. This property list setting data that we could pass got stored on the heap, and it was also written to disk within another plist here. And it would be reloaded each time CoreAudio daemon restarted, which was kind of interesting. So we both had the ability to spray in memory, and then would also get reallocated every time it restarted. When we're looking at property list data types, there's a few different core foundation types that you can pass in a plist. The most interesting ones that I was looking at, since we want this indirection to our data, would be using the CF array type and the CF dictionary type. And then for actually storing our payload, the CF string and CF data types seemed like good options. The nice thing too, when these APIs are allocatingplists, you can actually specify a huge number of elements per plist. So you can have an array with like 2,000 strings in it, and it'll allocate it very quickly, and you don't need to make like a bunch of mock message calls, which is kind of a nice allocation primitive. So the improved exploitation strategy then became, okay, first we're assuming we have RCE in some sandbox process, for example, Safari. Now we want to call this API where we can pass a plist, and we're going to have an array of a bunch of CF string objects. Then we want to trigger the type confusion vulnerability, not to try to exploit it yet, but just to crash and restart the process. And then it will reload from that plist stored on disk the data that we previously allocated. And we're going to hope that this engine object that we saw was using that uninitialized data got allocated within the memory of our old plist. And then we will trigger the type confusion again attempting to get the program to make a call with our previously allocated CF string. And then this is definitely not deterministic, so we're going to need to repeat steps 3 and 4 until it works. But since we're a local attacker, we kind of have as many tries as we need here. So to kind of help visualize this, we have our array of CF string pointers. Each of these is pointing to a CF string. It starts with that CF runtime base header, and then if it's a mutable CF string, we actually get a pointer to the raw bytes, which is really nice. If it was immutable, often they are inlined, the data is inlined. But in this case, we got a pointer to raw data that we could control. So then we hope that our engine object here in red gets allocated over that previously what was an array of CF string pointers. And then we know those last 2 bytes are going to get zeroed out. So they're not actually going to point always to the CF runtime base header, which we can't control. Sometimes they're actually going to point directly to our pointer to raw bytes if we get lucky, and that is 16-byte aligned perfectly. And it turns out if we allocate objects in enough of them and in the right way, we actually do get this to happen every once in a while. So this is a script that I wrote to dump all of these HALS objects on the system, and this is showing here that the pointer at offset 68 was zeroed out to point to data that I controlled. So once that's dereferenced, we see one of the allocated CF string objects, which is pretty cool. So the next step here was to build a ROP chain. We have our entry point here. It's calling offset hex 168. So placed a stack pivot gadget there, pointed it to the rest of my raw data pointer, and then could start the rest of the ROP chain there. And here I'm just writing opening a file in a directory that only CoreAudio daemon can control. And then here's what this looks like when it actually gets put into memory properly. One important thing I learned here when abusing CF strings is you want to use UTF-16 because if you're trying to pass raw memory addresses as UTF-8, it's going to break things. And so I was having a lot of hassles getting through that. But once I encoded them properly, they did show up really nicely in memory. There are some bytes that UTF-16, if you're too high, they will break things. And especially since it's writing to another plist, I had to kind of mess with things a little bit there. But eventually got the ROP chain properly wrote to memory. And if we get lucky, we will get that indirect pointer that points to our data, and we can hijack execution to our ROP chain. Okay, so let's try to do a demo here. Hopefully it works. As I mentioned, this is definitely not going to be deterministic, but I said my prayers before, and hopefully it'll work. Okay, so we saw I ran this before, and it did work. Right now, I'm running as myself. I'm going to switch to a root terminal real quick and remove our flag from this directory. So this directory is where CoreAudio can write to. This is where that system settings plist lives as well. Whoops. So let's remove that so that we'll know when we actually write the payload. So, whoops. Okay. So we're running as Dillon Franke. Just to show you, this user cannot write to that folder. So permission denied. Perfect. And then I already ran if we go to that directory again, you can see I already ran the heap spray because it does take a little bit of time. And all of those objects that I allocated are being stored in that system settings plist. So it's 35 megabytes, so there's quite a bit of data in there. If we look at the XML, there's our UTF-16 encoded payload. There's our ROP chain. Okay, so now what we will do is go back here. Just going to run script here that will check to see if our payload is in that directory. It's going to try to trigger the vulnerability. This is just saying trigger that type confusion vulnerability. Then sleep, wait for CoreAudio D to be restarted if it didn't work. And then sometimes we can get into a weird state when we trigger this where that plist that gets stored to disk gets destroyed, and so we actually need to regroom the heap and restart. But let's see if this works. So we will let this go. In practice, it works anywhere from after like 1 to 50 attempts in my experience. So we might have to give this a moment. But basically what it's doing here is enumerating all of the engine objects. So it's using an API to loop through all of those objects in the linked list. Then it's choosing one of them at random and hoping that it got allocated within our previously allocated pointer to buffer. Then it's triggering our vulnerability, and then sleeping to let the CoreAudio D service restart if it needs to. Okay, let's go back down here. And it's choosing, there's anywhere from like 3 to 10 engine objects on the system at any time, so it's randomly choosing one of those. And hopefully, eventually, it will execute our ROP chain. We'll let that run in the background maybe, and I'll go to a last couple of slides here. Whoops, and I do have a video here if it really never works. Perfect, so that was the type confusion CVE. The fuzzer additionally found a double free vulnerability that just got patched like a few days ago actually on May 16th, which is cool. Can't talk too much about that yet, but there'll be more info coming on that one soon. So I mentioned before that a bunch of the tools you use for this research are open sourced. So you can see those in the Project Zero tools repo. The fuzzing harness is there, as well as the custom instrumentation I mentioned, and a POC crash for the type confusion CVE. And then additionally, just published a blog post about building the fuzzing harness last week that you can read if you're interested. So I hope, and we'll check on this exploit here in just a minute, hopefully it worked. Hopefully I showed the power and importance of sandbox escape vectors to you all. I was trying to drive home this idea of knowledge-driven fuzzing as a great auditing method for vulnerability research, balancing that automation and manual analysis, and showed exploitation of a type confusion vulnerability in CoreAudio D, and hopefully inspired you to perform some security research of your own. I do want to give a big thank you to Ned Williamson, who is not here, but he's been at OffensiveCon in the past, and Yvonne Fratrick, who've been wonderful mentors, and also my fiance Isabel, who's been a great support to me. And let's check on this exploit. Okay, it's still running. Unfortunate. Okay, well, it's going to keep going. Eventually, it will find our ROP chain, but like I said, it's non-deterministic and can take a little bit of time sometimes. For now, though, we can let that run in the background. Happy to answer any questions that people have.
Hi, Dillon. Great talk. I was just wondering, like, did you ever, like, is it possible to debug CoreAudio D with LLDB? And if so, did you ever have to do it, like, anytime during your research process?
To use LLDB for debugging?
Yeah, to attach it to the CoreAudio D service.
Yes, definitely. You can definitely do that. I did that a ton when writing the exploit and when researching. You just need to disable SIP on your system, which you can just do by booting into recovery mode. But yeah, then you can attach to system daemons. Very helpful. And yeah, that's how I actually harvested all of those organic Mach messages when I was building my initial fuzzing corpus. I just wrote a Python LLDB script that would hook onto that and start dumping them. So yeah, great way to do it as well. And I had like an initial V1 fuzzer that was just like flipping bits with LLDB And that was kind of like an initial proof of concept fuzzer that I wrote.
Thank you so much.
Oh, look, it worked. That's cool. Thank you. I said my prayers, so I'm glad that worked. And as you can see here, that was wrote by CoreAudio D, which we didn't have permission to. Awesome.
Hey, thanks for the great talk. So actually, do you use any plugins for LLDB?
Sorry, what was that?
Do you use any plugins for LLDB?
I haven't really used too many of the LLDB plugins. I just used LLDB Python initially when I was experimenting with it, but kind of moved to using TinyInst after that, just because it's a lot easier to customize things, in my opinion, and was using it as well for Jackalope, so I had a pretty good understanding of how it worked. But it can be a great tool as well.
Mm-hmm. We released Pawn Debug for LLDB. If you have heard about that, that's like a plugin for GDB, but it also works for LLDB now. So yeah.
Oh, fantastic!
You may need. I mean, you may find it useful. Yeah. Thank you.
Awesome. Thank you.
Hi. Does this bug also work on iOS or just on macOS?
That's a great question. I have not tested it on iOS, so I can't speak to that, but iOS, as far as I'm aware, does use the CoreAudio framework. And I believe, don't quote me on this, I believe they did release a patch for iOS. We can look back at that, but it should. It should.
Thank you.
Great question. Perfect. All right. If there are no more questions, thank you all so much for listening.